It's a pleasure for me to tell you about a project that we currently have on a completely new way to make composite material based on frontal polymerization of the matrix material of the polymer. This will be a much faster and energy efficient way to manufacture these composites compared to what is currently being done. As you will see, this is a multidisciplinary project that involves a lot of students from various departments. I've been working with two colleagues of mine on this, Professor Nancy Soros, who's in material science and engineering here at Illinois, and Jeff Moore, who's a professor in chemistry at Illinois. This project is being funded right now by the Air Force Office of Scientific Research and the National Science Foundation, and is centered among the Autonomous Materials Systems group located at the Beckman Institute at Illinois. We have a very large group of students and postdoc working on this project, and you have here their names and pictures. Those that are listed in blue are those working directly in my group. In this project, we focus primarily on the modeling aspect of this new way of making composite materials. But as you will see, I will present a lot of experimental results as well. So just to get started, most of you are probably familiar with the challenges associated with composites. We know the composite materials are very promising materials and are used in a wide range of applications, including obviously aerospace with 787, or the wind energy industry, as many of the turbine blades are made out of composite material. Now, one of the key challenges in the wider use of composite has been the complexity and cost of making complex composite parts. As you see in the bottom two pictures, you'll see on the left an autoclave that is currently being used to cure very large composite structures, and on the right, a heating mold that is used for the manufacturing of wind turbine blades. The conventional way of making composite material, let's say in an autoclave, involves a long and fairly complex temperature and pressure cycle that can, take multiple hours and bring the parts at temperatures of the order of 165. So there's a major energy and cost associated with the manufacturing of these composite parts, and also a carbon footprint. And so the objective of this project is to substantially reduce this cost and really change completely the way composite materials are done. So you have here on this graph, on the y-axis, the energy consumed per volume, and on the x-axis, the time to cure per volume. The conventional way of making composites is listed on the kind of represented on the top by the two black squares over there. As I mentioned, conventional bulk curing process involved multiple hours. Now, obviously, since we plot the time to cure per volume, well, the larger the parts, the smaller this number. But what we would like to achieve is to reduce the energy consumed by many orders of magnitude. We're talking about 6 to 8 orders of magnitude of compared to conventional methods, and at the same time reduce the time for the curing process by about a factor 100. And at the same time, we would like to achieve this cure outside of an autoclave. The basic method that we propose is the frontal polymerization, which is schematically represented here. So the idea is to introduce into the polymer a latent catalyst that basically is completely inactive until you introduce a small thermal trigger, typically in the form of a very small amount of heat. And that latent catalyst becomes active. And as it becomes active, it starts the polymerization, which is exothermic, and therefore creates its own heat, and therefore allows more of the monomer to to be polymerized. Now, we did not invent frontal polymerization. It's been shown to be applicable to a range of material systems, as you can see on the top right, from epoxies to acrylates. Now, the system that we decided to adopt first is dicyclopentadiene. The reason for this is that we had a lot of familiarity with this particular system, because that's the one we had used previously in making self-heating materials. That's the heating agent that we had decided to adopt. And so that's the first polymer system that we've adopted. There are various ways of triggering this frontal polymerization. It could be in the form of a thermal trigger, a photo or chemical type of triggers. And so if I can represent this graphically or schematically, what you would have is the propagation of a polymerization front, as shown in the middle picture here. At the bottom, you can see that ahead of the front, we have either a liquid, so a monomer, or a gel state. And after the front passes by, we have a fully polymerized polymer. Now, this animation here will illustrate what the frontal polymerization process is about. So we have a relatively small amount of dicyclopentadiene, which is in the liquid form originally, right? So it has more or less the viscosity of water. And we introduce a small amount of heat in the form of joule heating associated with the current that passes through the wire embedded on the top. So we introduce it just for a little bit, and then we just let the front propagate. So ahead of the front, we have a very liquid monomer. Behind the front, we have a fully polymerized solid that would have the stiffness of about 3 gigapascal, which is typical for polymer systems. And the idea is that we can actually make this with about 6 joules of energy in about 78 seconds, which is substantially less than what it would take if we were to use a bulk polymerization in, let's say, an autoclave type of system. Now, from a modeling perspective, the way we describe the system is using the coupled partial differential equation you can see on the top left, which are written in terms of the temperature, capital T, and alpha is the degree of cure. The degree of cure is a quantity that captures the evolution of the material during the polymerization. Alpha equals 0 is the monomer, alpha equals 1 is the fully polymerized polymer. And the coupling is associated with the term rho HR d alpha dt, which is the term that corresponds to the heat generation associated with the exothermic reaction. D alpha dt is described in the second equation, and that's the pure kinetic model that is extracted from measurements, from the DSC measurements of performed on this polymer system. And then typical values that you have in this model are listed on the right-hand side. The material of interest, as I mentioned, is dicyclopentadiene, DCPD, with Grubbs catalyst. One key aspect of one key contribution that we've made to this process is the introduction of phosphide as inhibitor. The idea here is to introduce a very small amount of phosphide that allows the monomer to remain inactive, or the catalyst to remain inactive for a substantial amount of time, so we can actually manipulate the the monomer and before we really trigger the frontal polymerization. And you will see an example of that a little later. So the challenges from the modeling point of view are associated with the fact that this is a multi-physics problem. We solve for both the temperature and the degree of cure. It's a nonlinear system of equation. It's transient. And especially we have very high gradients of temperature and degree of cure in the immediate vicinity of the front as it propagates through the part. There are various ways that people have proposed to model this from a continuum perspective. The Italian group in 2005 used a finite difference approach. We decided to use a finite element approach based on MOOS, which is the multi-physics object-oriented simulation environment that was developed at Idaho National Lab, which gives us the ability to adapt the mesh. As you can see in the figure on the right, you can see that the mesh gets refined automatically as the front propagates the part. So this, this slide here will show a typical picture of an animation of the evolution of the temperature theta, which is in a non-dimensional form. So T is the temperature, T0 is the initial temperature, and T max is the maximum temperature behind the front, associated with the front, and it's simply given by the relation that you have right over there. Alpha is the degree of cure, which, as I mentioned earlier, goes from 0 to 1. And you can see in this animation that after some transients where we start the chemical reaction, the front propagates in a very steady fashion. The first front is obviously the temperature front, follows by alpha. The black curve corresponds to the degree of cure. And so we can also achieve this frontal polymerization in a gel. So here's an illustration, an experimental illustration of a gel that has been shaped in the shape of a cylinder. And then you can see the front that propagates to the entire part. And after the front has propagated, we have a fully polymerized one, as you can see right over here. So we have a very stiff type of polymer. Now, at the same time, we've developed a steady state solver. The idea is to allow us to make a faster link between the cure kinetics, so the description of the chemical reaction, and the properties of the front in terms of the speed of the front and the length scale associated with the front. And so here are the equations that I just described earlier. We first normalize these relations, and then we write all the equations in terms of a coordinate that moves with the steady state front. And we end up with a system of ordinary differential equation instead of partial differential equation, allowing us to solve for the speed of the front and the length scale associated with the process. And so here's a typical result that we get that look very similar to the movie that we just saw earlier. So on the left side, you have the description of the thermal front, the solid curve, and the dash curve is the degree of cure. For the case of alpha 0 equals 0, meaning there's no initial degree of cure. On the right-hand side, you have the similar kind of plot, but for the case of alpha 0 equals 0.2. So we're talking about a partially cure or a gel system. So the big advantage of the solver that we've developed is that it allows us to greatly reduce the computational cost and to create a direct link between the kinetic parameters and the front characteristics, which are the front speed and the characteristic length. Talking about these characteristic length, you have here typical snapshots of the front as it propagates, and there's a length scale associated with the thermal gradient or the thermal front and the degree of cure front, L alpha and L theta respectively. And we can use different ways to define these, and the one we decide to adopt are the one on the right-hand side, which are typically the kind of length scale that are introduced to define the length scale associated with a shock in fluid mechanics, for example. And so what we can do is we can, for example, obtain the variation of these two length scale with respect to the initial degree of cure alpha 0, as you can see on this figure. And you can see that as the front, as you pre-cure the polymer, meaning as you have a gel that is more and more pre-cured, you can see that the length scale, the front become less and less sharp. So the length scale increase as a function of alpha 0. We can also, using this model, capture the effect of, for example, one of the parameters that end up that shows up in the cure kinetic model, which is the activation energy E, and we can plot the variation of the speed of the front and the variation of this length scale associated with the degree of cure front with respect to E, right? So these are ways to quickly make the link between the cure kinetics and the properties of the front. So that's for pure DCPD. What we are interested in is use this technology to make composite materials. Now, we expect that the presence of the fibers will have a strong influence on how the front propagates in this material system. Now, if you look at the little part over here, right, of DCPD, well, if I try to do the simulation of this particular system, so if I have a piece of glass, this is a glass container, this is DCPD, this is an axisymmetric simulation, right? So what we see is that the front propagates in a fairly straight fashion, as observed experimentally. Now, if we start to introduce a carbon fiber toe, we know that carbon fibers are much more conductive than DCPD. So we expect that heat conduction through the carbon fibers will affect the speed and the shape of the front. And indeed, if we do a simulation, we introduce a carbon fiber toe in the middle of the specimen, we can see that very quickly the increased thermal conductivity in the fiber toe affects the shape of the front, as observed once again experimentally on the bottom right figure. And we observe that the front goes faster in this kind of model system. So obviously the next step was to apply this kind of technology of frontal polymerization in the manufacture of composites. And here's the way we've actually done this, right? So we first infuse the carbon fabric with liquid DCPD resin using a classical Vardon type of approach, vacuum-assisted resin transfer molding. And then introduce, as schematically illustrated on the top, you introduce a little bit of heat using an embedded wire. We introduce a certain amount of heat, and then we basically turn it off once the front starts to propagate, and the front will actually propagate to the entire part, and you will end up with the fully polymerized, fully cured composite panel. So what you have here, what you're going to see here is the evolution of the temperature. This is an actual experiment using an infrared camera for a fairly small, 10 centimeters by 20 centimeter panel. We introduce a little bit of heat using an embedded wire, then we just turn it off, and you can see that the front starts to propagate in a steady fashion through the entire part. We managed to cure this entire panel in about 2 minutes, once again, to be compared with the multiple hours that you may need if you use a conventional bulk polymerization technique, right? And we can make various types of panels, and the panels that we managed to make here is a slightly bigger panel that was made. We can also make corrugated parts. And if you look at the quality of the composite that we can make for this particular system, we can see that this is a pretty good quality. The void volume fraction is less than 0.2%. For this particular technique, we managed to make fiber volume fraction of the order of about 50%. We've since then, using a certain compaction type of approach, we managed to make volume fraction that are higher than this in excess of 60–65%. So how good is the material that we make using this technique? Well, first we looked at the mechanical properties of just the polymer itself, the DCPD polymer. So on this graph here, you have 3 different types of situation. On the left side, we look at the properties of frontal polymerized DCPD. The 2 middle bars correspond to the oven cured DCPD, and on the right side, you have the properties of epoxy, done using a conventional approach. The blue bars correspond to the Young's modulus, and the red ones correspond to the tensile strength. And what we observe here is that the properties of DCPD made with frontal polymerization are pretty much identical to those made to oven cure. And there are, well, the stiffness is a bit less than what you would have for epoxy, but overall the stiffness and strength properties are fairly similar to conventional curing methods. A key difference between DCPD and epoxy is that DCPD is much tougher than epoxy. That's a well-known fact, right? DCPD has been used to make structural components for various types of application, and DCPD is about almost like 3 times tougher than epoxy. Now, looking at the mechanical properties of the DCPD carbon composites, so a series of tests were conducted, once again, for the same 3 systems. On the left, you have the Young's modulus and the tensile strength for a composite system made using a conventional bulk polymerization approach. In the middle, the one made through through frontal polymerization, and on the right, the kind of reference, which is a carbon epoxy system. And what we observe here is that, once again, the properties are relatively similar. Now, the tensile strength is a bit less, right, than what we would get for an epoxy system, as shown by the red bars over here. However, it's important to remember that carbon fibers have been optimized through a series of sizing systems, have been optimized to interact with epoxy. We use the same fibers, so we have not really optimized the interface yet, and that's part of the current research activities. The objective is really to find the treatment of the carbon fibers that will really strengthen the bond between the carbon fibers and the and DCPD. So, from the modeling point of view, modeling the frontal polymerization in composites is basically the simplest model we came up with is based on exactly the same type of coupled partial differential equation, the same one as I showed before for pure DCPD, except that now we use the average thermal properties and densities or the homogenized one for the unidirectional composite system, right? So the quantities with the overbar correspond to the homogenized properties. And for this simple problem, or the simplest way to approach this, is simply use the rule of nature for that particular quantity. Now, the fiber volume fraction, which is denoted by phi, enters also in the term associated with the exothermic heat of reaction. Obviously, the more fibers we have, the less matrix we're going to have. And therefore, we have a term 1 minus phi that will kind of scale the heat generation associated with the exothermic reaction of the matrix. The second equation is absolutely identical to what we had before. Now, there's a major difference between the thermal properties of the matrix and the thermal properties of the carbon fibers. And you can see here, it's almost 2 orders of magnitude difference. So as you increase the fiber volume fraction, the homogenized thermal conductivity of the composite increase quite drastically. There's also an increase in terms of the density, but that increase is not as high. So if we use this particular model and we actually solve these partial differential equations, here we obtain these results. So on the left, on the top left, you have the variation of the speed of the front as a function of the amount of fibers, so the fiber volume fraction phi. Phi equals 0 corresponds to the pure resin case. And what we obtain using the model is that as we increase phi, the speed of the front will start by increasing, reach a maximum, and eventually start to decrease afterwards. If we look at the evolution of the maximum temperature, we can see a steady decrease in the maximum temperature behind the front. The bottom left figure shows a snapshot of what the front looks like for 3 different values of the fiber volume fraction, from 0 to 0.25 to 0.4. And what we observe is that due to the added thermal conductivity created by the fibers, right, what we observe is that the front becomes less and less sharp, becomes more and more smooth. And so we basically, to try to explain these results, well, it makes kind of sense that we have 2 kind of regions or 2 parts to the response in terms of the speed of the front. What we observe first as we increase speed is that the term that is kind of influencing the solution is the one associated with the added, or the increased thermal conductivity of the composite. And therefore, since there's an increased thermal conductivity, the front will propagate faster. But at some point, as we increase the fiber volume fraction further, we can see a steady decline in the speed of the front because of the fact that there's less and less heat that is generated by the chemical reaction, since we have less and less matrix. So now, if we can actually quantify the increasing role of diffusion by just comparing the numerical value that I just presented for the maximum temperature as a function of the fiber volume fraction. So these are the square symbols to the very simple analytical relation that we obtained right over here, which ignores completely the role of diffusion. And if we compare these two, we can see that the analytical expression follows the numeric one very nicely, except when you start to increase the fiber volume fraction to values in excess of 0.3, let's say, we can see that they start to deviate from each other. And that's really due to the diffusion that takes place, the increased importance of diffusion associated with a larger amount of fibers in the system. Now, how does it compare with experiments? So you have here these two quantities, right? The speed of the front versus fiber volume fraction on the left, and the maximum temperature versus fiber volume fraction on the right. And the black symbols are the numerical models that I just, or the 1D result that I showed, that I presented earlier, and the red square symbol correspond to experimental observations. And we can see that the model captures the basic trend of the experiments, meaning first the increase and then followed by the decrease in terms of the speed of the front versus the fiber volume fraction. However, it tends to overestimate, to overpredict the values that are observed experimentally. And the reason for this is that the 1D model is, by definition, adiabatic, meaning it ignores the amount of heat that is lost to the surrounding. And to capture this, we perform a series of two-dimensional simulations, which are shown right over here. So on the top and the bottom, you have the support, which is a foam type of material that we use in the experiments. And in the middle, you have a layer of a composite system. And we can see that as the front propagates through the composite, it actually loses some of the heat to the surrounding, as you would expect. And so if we actually look at these results and compare that to the experiments now, we can see that these 2D results captures the experiments much more closely, especially with regards to the speed of the front, a bit less in terms of the maximum temperature. We still overpredicted a little bit, and we believe that the reason for it is that the experiments, the location of the thermocouples that were used in the experiment is actually more closer to the interface between the support and the composite layer. So obviously this technology could be used also for glass fibers. Right? Glass fibers are much less conductive than carbon fibers, so their effect on the speed of the front is substantially less than what we observe for carbon fibers. Carbon fibers are in red, glass fiber results are in blue. With regards to the maximum temperature, it doesn't make that much of a difference. So that summarizes my the presentation. I hope I convinced you that the frontal polymerization, or we call also FROMP, which is frontal ring opening metathesis polymerization, which is the chemical reaction that takes place in this case, offers a promising new way to make thermosetting polymers and composite materials in a much more rapid and energy efficient way. The process can be modeled using a coupled thermochemical reaction diffusion equation. So on the right, you can see an animation that was done for the interaction between two fronts. The top two figures correspond to an experiment that was done where two fronts were started from the left and the right and joined in the middle. We know that as the front merge, we can see that obviously the heat has nowhere to go. So we predict, we observe and predict a thermal spike. And we're looking at ways to alleviate this particular effect. Another thing, and I didn't have time to talk about it, but this is a whole new area also where we believe frontal polymerization could play a very important role, is in 3D printing. So this method allows us to really make free-form, three-dimensional features, such as the one you can see in the animation. So we deposit here a gel of DCPD gel, and you can see that as soon as you deposit it, you have the front that follows that that follows the needle, and we can actually make, using this technique, a material that is polymerized right on the spot, and we can make different types of shapes. With regard to current activities, we're looking at, as I mentioned, the merging of different fronts, and also we're looking at FP-driven instability. So in most cases, the front propagates in a very steady fashion. But there are some conditions in which the front does not propagate in a steady fashion, but more in a pulsating type of way. And the idea is, can we use this kind of frontal polarization-driven instabilities to what is called morphogenesis, to create in an artificial way, in artificial fashion, a methodology or technique in which we can make objects with different shapes that eventually are created in a completely autonomic fashion. So the kind of motivation for this is illustrated at the bottom left, which shows the evolution of how fingers are created in biological system, in this particular case, in a mouse. And so the idea is, how do we go from this more like spherical structure that you have on the left to something that has a series of fingers? And can we represent this in a, can we achieve this using this reaction diffusion equation and these kind of instabilities to make material with truly unique properties? So this is more like a fundamental research point of view. But this opens a wide range of new areas. So for more information about this particular project, I would encourage you to look at the paper that we published in May 2018 in the journal Nature. And this kind of provide a very good overview of the capabilities of this particular technique. And don't hesitate to contact me if you have any question. So to close, I'd like to use this opportunity to thank all the members of the Autonomous Materials System Group that is here at Illinois. You have here the picture of all the members of that particular group. And in particular, I would like to recognize the key contribution and leadership contribution of our former colleague, Scott White, who unfortunately passed away this past spring. And so with this, I end, and I thank you very much for taking the time to listen to this. And as I mentioned, if you have any questions, don't hesitate to contact me.